5.4 Exponential function. How do we take the derivative and the antiderivative of any given exponential function? So the natural exponential function y equals base e to the x. If you look at y equals e to the x, as x approaches infinity and it's increasing, when x goes to negative infinity, the y value will approach 0. So these two limits here. And the derivative of e to the x is e to the x itself. E to the u, we have to use the chain rule. And the antiderivative give itself, and e to the u, du give us e to the u. So this is what we need to do for u substitution. And the properties, e to the a times e to the b equals e to the a plus b, and e to the a divided by e to the b give you e to the a minus b. Same property also apply for any other base. So let's have a look at some of the examples. Example 1 and 2 find the tangent line to the equation at the given point. So now you can pause the video and try to do it yourself, and you can compare with my answers later. When you look at example 2 here, you have to be very careful. E to the third power, this is just a number. When we take the derivative, you don't have to take the derivative of e to the third. Next example will be implicit differentiation. You can pause the video and compare your answers later. This is the solution to the implicit differentiation. So when we take the derivative of 10, give us 0. Be very careful here. Next, I'm going to show you some examples. How do we use u substitution to solve antiderivatives of exponential function? For example, this one. We're going to define our u equals negative x to the fourth. So du equals negative 4x cubed dx. So this problem will become e to the u times du. Give us e to the u plus c. Now we replace u using negative x to the fourth plus c. Similarly, this one, u equals e to the x plus 1. So du equals e to the x dx. This is u squared du. U cubed over 3 plus c. So it's e to the x plus 1 cubed plus c. And the next one. This one, if you look at this, we only have e to the x in the denominator, and we have e to the 2x, e to the x here. It will be easier if we split this into 3 different integrals first. Plus integration 1 over e to the x dx. So now e to the 2x over e to the x give us e to the x dx plus 2 dx plus e to the negative x dx. This gives us e to the x plus 2x minus e to the negative x plus c. Now you can pause the video for 5 minutes and compare your answer with mine for part A and part B, and also how do you use definite integral to find the area using antiderivatives. Now you can compare your answer with mine for part A and part B. For the area part, when we integrate this, if you change your variables, part A, you don't have to do the u substitution. For part B and part C, if you do the u substitution, you can also, after you replace everything using u and du, you can also change the boundary to u. How do I get the new boundary? I plug 0 in, 1 plus e to the 0, and e to the 0 equals 1. So the lower boundary is 2, and if I plug 1 in, the upper boundary is 1 plus e. And then I can simplify a little bit here. For part C, similar, we use u substitution. I change the boundary to u. You don't have to, if you don't want to change the boundary for u, from here, you are going to replace u using e to the x. You don't have to change the boundary. It will give you the same sine of 1 minus sine e to the negative 1. Same answer. It's up to you.